Hello, pre-calc students. This is going to be the start of a new unit. We're starting Unit 7 here, and Unit 7 is all about logarithms, logs, as we affectionately call them. So today we're going to really just explore some of the basic properties of logarithms and different forms that we can write equations in. We have exponential form, which we'll be very used to from Unit 6, and then we're going to talk about what that might look like when converted into a log form. And just get some practice to start today converting back and forth between these two formats. Logs are pretty essential to us because logs are the inverse operations of exponentials. So when we talk about logs, what is a logarithm? It's something that undoes an exponential function. Just like multiplication and division are inverse operations, subtraction undoes addition. We need something to undo, raising something to the x power, and what that is it's going to be a logarithm. So the exponential form that I want you to write down here is b to the e equals capital N. And I think this information in the exponential form will make sense when I tell you it's a base raised to an exponent equals some number n. And the form that I call this over here is Ben form, right? Looks like it says the name Ben. Whereas in log form, what I'm going to write down is log base b of n equals e. So you can see how when I translate from exponential to log form, maybe where some of these values go, the base of the exponential is now the base of the log. And I'm taking log base b of a number, and what that does is it equals the exponent that was up here. So like I was just saying, the log is the inverse operation here. It undoes this exponential form to return an answer that is an exponent. So what we're going to do right now is we're going to practice converting between these two forms. And the first thing we'll practice is going from exponential to log form. So for some examples here, let's take a look at 2 to the third power equals 8 and what that would look like in log form. Well, if we have 2 to the third power equals 8, this is currently in Ben form from up there. Base to this exponent equals the number. To convert to log form, it's going to be log base 2 of the number 8 equals 3. So the way we evaluate logs is we're saying 2 to what power over here would equal the argument on the inside, which is 8 there. So 2 to the third power is what we would do to get 8 in that instance. If you have 1/2 to the negative fourth power, that would equal 16. So if I were to write this in log form, I would say, well, it's log base 1/2 of the number 16, and that equals -4. So it's just getting some practice writing back and forth between these two forms. And some of your homework tonight will be practice just like this. If I gave you something of the form we're starting with exponential 10 to the 5th equals 100,000. In log form, that would be log base 10 of 100,000 equals the exponent of 5. And by the way, log base 10, we'll get into this later in the lesson, but we may not write that base 10 there at all points, because when you don't write a base, we're kind of assuming that we're using base 10. That might sound familiar from last year. All right, let's switch over to the other form. If I want to convert from log form to exponential, so convert from log to x, oops, we need an x there, exponential form. So if I gave you something of the form log base 3 of 27 equals 3. The nice thing is that if you're unsure whether or not you've converted to exponential form correctly, just check on your calculator or check in your head to see if that makes sense. This is now in, oh, I didn't even tell you. Hold on a second, guys. I call this Ben form. I call this over here kind of Benny form, Ben and Benny. And sometimes that helps students. I'm not sure, but if you look at the base number exponent, Benny is maybe how you would read that. So if it helps to think about converting from Ben to Benny, or having Benny now and converting back to Ben, here's what we've got. We've got base number exponent, right? If I want to write this in exponential form, it would be 3 to the third power equals 27. And that's certainly a true statement, that 3 to the third power is 27. Now, there wasn't a lot to mess up there, I guess, if the base and then the number on this side are the same. But when some of those things change, just to make sure that we have a statement in the end that makes sense, log base 5 of 1/25, I'll tell you that that equals -2. So the exponential form would say the base of 5 raised to that exponent, -2, equals the number inside the log of 1/25. Okay. And maybe just one more, log base 3/4 of 1. And log base 3/4 of 1 is actually going to be 0. And this will be another property that we talk about later on in today's lesson, because when I take 3/4 and I raise it to the 0 power, that's how we're going to get 1 again. So there's kind of a special property happening in that last example that we'll recap later on. Lots of things coming up later on in the lesson, but some things to pay attention to. All right, now that we've done some properties where we've converted between log and exponential form, I want us to be able to evaluate some logarithmic expressions and determine what the answer is. So when I say to evaluate, it might be something like log base 8 of 4. So to evaluate log base 8 of 4, what I would recommend doing is saying, well, we know it equals some number, and you can call it n, you can call it x, whatever you want. Okay. In order to evaluate logs, if it's not an easy value for you to think of, this is the exponent to which we raise a base of 8 in order to get the value 4 right there. If that's not easy to come up with, convert this to exponential form and then solve that exponential equation. So in exponential form, this would say 8 to some number x equals 4. And then now that I have it in this format from our exponentials unit, hopefully we're thinking common base. I could do 2 to the 3rd on the left side and 2 squared on the right side. So therefore, if 3x equals 2, x would equal 2/3. Now, we added x in here. This was not really a solving of an equation. We put an x in there just so we can come up with the value in the end. So just be careful when you introduce an x here. It doesn't seem like a big deal, but the value for log base 8 of 4 is just, in fact, 2/3 is the answer there. 8 to the 2/3 power would be 4. Let's try another one of those. So if I gave you something like log base 1/27 of 81. If we're not sure what number this is, such that when I raise 1/27 to that power, it equals 81, let's set this up in a format similar to number 1 over here, where we convert to exponential form. 1/27 to the x equals 81. And now this is a question we could have seen very easily back in our exponentials unit. So let's see, base of 3 seems like it would make sense to me with the 27 and the 81. This is 3 to the -3rd power. If I change 1/27, this is 3 to the 4th power. So if -3x equals 4, then x equals -4/3. So the value for log base 1/27 of 81 is -4/3. Okay. So we will do a lot more practice like that when I see you in class. So we'll get there. But just to kind of get an idea as to how do we even evaluate logs, it's good to get some practice there. Let's just do one more, actually, because it's an important concept. Let's do one that I'm hoping you can do without even setting up that equation that I was just showing you. Okay. So without even saying let this equal x and convert to exponential form, think about this. 5 to some power has to equal 25. So what is the exponent, which we raise a base of 5 to get 25 as our answer? Well, the answer there is, oops, yeah, just 2. I got all excited. It's just 2, right? 5 squared would be 25. So log base 5 of 25 equals 2. I want you to become a lot more confident being able to, this year in pre-calc, evaluate logarithmic expressions without converting to exponential form every time, without using a calculator, things like that. Here's just one more, log base 32 of 32. So 2 to some power has to equal 32. I mean, this one might take you a little bit longer in your head, but if you know, like 2 cubed is 8 times another 2 is 16 times another 2 is 32. Well, log base 2 of 32 is going to equal 5 because 2 to the 5th power is equal to 32. Okay. So a little bit more practice with evaluating logs there. It's just good number sense to know what the answer to a log is. It's the exponent to which we raise that base to get the number on the inside. Okay, let's go back to some of the things we were talking about earlier. I'm going to talk about some special bases here. And earlier we had something with log base 10 in it. So if you have log base 10 of a number, that's known as a common log. And because it's a common log, because we work in a base 10 number system, we actually usually don't even write the base 10 in there. So you might just see that written as log x. In fact, you know where the log button is on your calculator, right? Here it is, right next to the 7. If you type in log of a number on the calculator, it's working in base 10 automatically. And I'll prove that to you in a moment when we do some evaluating with our common logs here. So for example, if I asked you, what is log of 100? Log of 100, I'm hoping you're saying is 2, because this is a base 10 log. So if I do 10 to the second power, that's 100. And like I said, I told you I'd prove it to you. Oops. So if you on the home screen of your calculator right now type in log next to the 7, right? Log of 100, it's going to tell you 2. We're working in base 10 because that's what number system we use, a base 10 number system. Okay, let's try some other there then. So if I said, what's log of 1,000? Log of 1,000 would be 3. 10 to the third power is 1,000. How about log of 0.1? That's a little weirder, but log of 0.1, the way I would want you to think about this is log of 1/10, right? As a decimal, 0.1 is 1/10, and 0.8, that's 10 to the negative first power. So the nice thing is if you can express that as 10 to the negative first power, right? This is log of 10 to the negative first. I'm asking you 10 to what power is 10 to the negative first? Well, the answer is -1. If 10 to some power has to give you 10 to the negative first, if you can get the base of an exponential and the base of the log to match, the answer is just that exponent on the inside. So that might be a good general rule of thumb moving forward to try and make those two things match if possible. It's going to make your life just that much more easier. So what about log of 1? So 10 to some power has to equal 1. The answer there is 0. And that kind of brings up a good point here just in general. If you have log base b of 1, it doesn't matter what the base is. It could be base 10, could be base a billion. It really doesn't matter. Log base anything of 1 is 0 in general. Because if you have that base b to the 0 power, no matter what the base is, anything to the 0 power is in fact 1. Okay. All right. What we're also going to get into is some other special bases in this unit, and we're going to deal with our natural exponent a little bit here. So if I were to talk about log base e of x, that's pretty special to us because base e, when we're talking about e to the x in exponential form, e to the x is a pretty special exponential function, in fact, based on the fact that it's the natural exponent. So because log base e of x is so special to us, log base e of x is known as ln of x, or ln is the natural log. And we're going to use ln quite a bit in this unit. You'll notice ln on your calculator is right below log because it is so special. Okay, the natural log is the inverse of e to the x, whereas log base 10 is the inverse of the function 10 to the x above it there. Okay, so if I were to ask you some questions evaluating with log base e, which is ln of x, if I said, what's the ln of e? The answer is 1. Because if this is log base e, e to what power is e on the inside? It's 1. Well, what about the ln of 1? ln of 1 is 0. Because log base anything of 1 is 0. And just a few more for practice. If I gave you the ln of e squared, similar to what we did with our base 10 example up there, you know, if the base of the log and the base of the exponential match, the answer is that exponent. So log base e of e squared is 2 because e to the second power is e squared. So it's nice if the inside has a base e already. Like if I call this e to the 100th, the answer is definitely 100. Okay. So it's nice to be able to evaluate quickly within natural logs, especially when there's some sort of base e already in there. Okay. So last thing we're going to talk, oops, hold on, sorry. Last thing we're going to talk about today is some properties of logs. And these are properties that you learned last year in Algebra 2, but it's been a while. So it's a good idea to recap them. Okay, so for some properties of logs, let's start with the product property. Okay, there are 3 of them. What the product property states is if you have log of a product, and it doesn't matter what the base is, log base b of a product, x times y, that would equal log base b of x plus log base b of y. So you can expand this expression, this product, into this format over here where you have log of x plus log of y, keeping that base the same. And there's going to be instances where we go back and forth between both of these formats. We might take this form where it's expanded and condense it to this version, or we might take that condensed version and expand it out this way. We'll go back and forth with these properties. We have something called the quotient property, just like we have the product property. So the quotient property would be log base b of x divided by y. And if multiplication expands out to addition, it probably won't be too much of a surprise that for the quotient property, we're going to expand that to subtraction. It's going to be log base b of x minus log base b of y. And finally, one of the most important rules, I don't want to say that these aren't important, but this one's pretty big to us. It's log base b of x to the y power. Okay, log base b of x to the y power. The rule here, this is really the one that undoes exponents for us, is you can bring that power all the way to the front of the log and write this as y log base b of x. And there's a good reason why that happens. It's not just magic. It's not, I used to call this the Angry Birds rule. I don't know if that's a good reference anymore, but think about like pulling the y back and slingshotting it to the front. I don't know if that will be a good reference or not. You'll let me know next time I see you. But anyway, why is this happening here? It's because when you raise something to a power, it's the idea of repeated addition, or repeated multiplication, I should say. And repeated multiplication becomes repeated addition when you expand. So you can write it in this form if you think of this as being repeatedly multiplying y times your log base b of x. That y is going to come out front when you add all those log base b of x's together. So there's definitely a connection between the product property and this property here, but this one's pretty big. Okay, this one we'll use pretty often when we eventually get into cases where we are solving log equations. Okay, so the last thing we should really do then is, now that we have those properties, is do some practice where we convert back and forth between those forms. So we're going to start by doing something where we expand some logarithms. And the first one that we'll look at is, let's expand log of x squared times y. Okay. So there are 2 properties we're going to use to expand this. One of them being that we're multiplying these quantities, the other being that we're raising something to a power. So when I expand this into, I'm going to separate it into 2 logs now. I know that multiplication separates to addition, and the other thing that's going to happen when I expand is that powers will drop into the front of the log. So this is going to be written as 2 log of x. Power comes out front. Multiplication in the next step splits up into addition, so plus log of y. And that is the expansion for this expression on the left side. And that's it. So make sure the 2 just belongs to the x, because only the x is being squared in there. So we don't want to make it belong to both terms. All right, if I have, let's say something like log of, let's do a squared times b over c cubed. Let's use all 3 properties now. So if we knew how to do this expansion, this one is just going to involve a few extra steps. We have multiplication, division, and we have exponents for some of those variables. So when I start expanding, on the top, multiplication will expand to addition, and this power of 2 is going to come down to the front. So it's going to be 2 log a. Multiplication now becomes addition plus log b, no power for b. And we can do this all at once at the end. When I divide by c cubed, it's going to be minus, but bring the exponent out front, 3 log c. And there's my expansion for log of that expression. Okay. All right, let's do maybe just one more there to kind of make sure we get the right idea. Let's see. If I gave you, let's do log of the square root of, let's just do x over y. I like that. Okay, log of the square root of x over y. So the property here is, well, when you have a square root, we can think of that as being an exponent. And what exponent is taking the square root of a quantity? It's raising it to the 1/2 power. It's not squaring it. Students sometimes want to say squaring it. Squaring it would get rid of the radical. But when I have a radical over a quantity, it's the same as raising it to the 1/2 power. So when you pull that 1/2 to the front, you have to keep in mind that it belongs to both the x and the y right now. So you can do this in one of two ways. You can take the 1/2 out front and write log x, division would become subtraction, minus log y. This is an acceptable answer. Or if you want to distribute the 1/2 in and write 1/2 in front of the log x, and because it belongs to both the log y, that would be okay as well. But both of these are equivalent answers, of course. So just make sure that you do one of these two formats and that you don't just apply the 1/2 to one of those variables. All right, last thing that we'll do today is condense some logarithms. So if I have something already expanded out, what would that look like when I go to condense here? So if I have 3 log base 4 of x, because we can use other bases, plus log base 4 of y. What would that look like if I condense this? So now I want to take, like I said, what I had on the right side here and work backwards, write it as a single logarithm. So when I write my final answer, I'm going to write log base 4 once and then open some parentheses and put the appropriate quantity on the inside. Well, when I work backwards, addition is going to become multiplication. And what happens to numbers that are out front? We're going to Angry Birds them back up here as the exponents. So this is going to become x cubed times y to the 5th on the inside. And if you feel like your expanding is a little bit stronger than condensing, think about expanding this. Would it get backwards to this expanded form over here? Okay, so not too many more of these. Let's try something. This would be the last one, actually. Let's do 1/5 log base 2 of x. And then we'll do minus 3 log base 2 of y. And we'll throw in another minus there, log base 2 of z. Okay. Okay, for this last one here, when you have those two minus signs, you're going to think about, okay, well, minus when I condense is division. And what's going to wind up happening is since we're subtracting this and subtracting this, both of these terms, when I condense, will just go into the denominator, okay? So I'm going to write 1 log base 2 here. And the only thing that's going to be on top of the numerator when I condense is x to the 1/5 power, which I'll may rewrite in a moment. On the bottom, this y cubed is going to go up. It's not y to the -3rd. The negative is what's making it go down in the denominator. And then when I subtract log base 2 of z, again, the idea would just be actually that you're going to put it in the denominator, but y cubed and z should get multiplied down there. Perhaps I can prove that to you by showing you that if you factor a negative out from the end of your expression, it would become a plus log base 2 of z. So writing it like this says, oh, I have to subtract, which means condensing to division, the product of those two things. So factoring out a negative, I think, helps to justify that. And then one last note about the numerator here. Sometimes I would write that as the 5th root of x instead of writing x to the 1/5. Just like I converted a radical to a fractional exponent here, sometimes if I have a fraction as the exponent, I convert it to a radical when I go to rewrite the condensed form. Okay, so we will do a lot more practice with log properties over the next few days, and log properties are pretty important to us because they are helpful in solving equations later on. So if you have any questions, let me know. Otherwise, we'll practice more next time I see you.